Hello student, hi, good evening. So today we are going to see how to find the Fourier transform of the sinusoidal signal multiplied by the unit step signal. Okay, unit step signal plus shifted version of unit step signal. Okay, so that is what, let's see here. I have one problem, so that is what, like x of t is a signal, so that is what sine, let us take this as cos omega t into u of t minus u of t minus 2. So this is my signal. Okay, so this is what cos omega t into what, into u of t minus 2. How to find the Laplace transform for this signal? Okay, so let's see here how to find the Laplace transform. So first of all, we should be very careful about this, that how we can make this. What is this signal? First we are going to draw this signal. Okay, so first if we draw this signal u of t minus 2. So what is this signal? Is starting from this u of t to what, to 2. So this is what, 2 0, and this signal is my u of t minus 2. Okay, so this is my signal. Okay, this is my one signal, and this is what, cos omega t means what, I am multiplying my cos omega t signal with this shifted rectangular type of signal. Okay, so this is what, so through this we can calculate the Fourier transform for this signal. If we calculate the Fourier transform by multiplying u of t separately, u of t minus 2 separately, it will become somewhat complicated. Okay, so that is why we have to draw first this one signal. From this we are able to understand that yes, it is a rectangular signal. Yes, for rectangular signal we know the Fourier transform for standard rectangular signal. Okay, if we know the Fourier transform for standard rectangular signal, then we also know the Fourier transform for this signal also. Yes, so which is a shifted version of standard rectangular signal. Okay, so let's see how to find the Fourier transform for. First we will find the Fourier transform for this, then we will find the Fourier transform for this, then after that you see multiplication in time domain correspond to what, the convolution in frequency domain. Okay, so that property we know very well. Okay, so that so let's see. Okay, so how to find first, and let me rub this also. So first I have what, I u of t minus u of t minus 2 signal. Okay, so which is my signal? This one 2, this 0 to 2, this is t, and this is my signal. Okay, so this is my signal now, and amplitude here is what, 1. As we know very well that standard rectangular signal which is varying from minus t by 2 to plus t by 2, so this signal with amplitude 1 with time t, the Fourier transform for this standard signal is what? What is the Fourier transform for this standard signal? That we know very well. What, let's say this is amplitude a here, and which is nothing but a t, yes, a t sync omega t by 2 pi, sync omega t by 2 pi. Yes, so this is my what, Fourier transform for this standard rectangular signal. What is this? AT sync omega t by 2 pi. Yes, so this is what, standard rectangular signal. This is the Fourier transform for this standard rectangular signal. If we know the Fourier transform for this standard rectangular signal, then we also know the Fourier transform for this. Yes, which is a what, shifted version. Yes, let's see here. Let me rub this. Okay, this is what, AT sync omega t by 2 pi. Okay, so this is the Fourier transform of standard rectangular signal. So let me rub this, then I will draw this signal here. If you see, this is my rectangular signal which is varying from minus 1 to plus 1. This is t, and amplitude is what, 1. You see, amplitude is what, 1. We know standard rectangular signal Fourier transform is AT sync omega t by 2 pi. Okay, 2 pi. Similarly, you see what is a value here, 1, to 1 into what is t value here, t value is 2, to into 2 sync omega, what is t, 2 into 2 divided by 2 pi. You see 2 get cancelled, and we get what? We get to sync omega by pi, to sync omega by pi is the Fourier transform for this rectangular signal. Okay, so what is this? To sync omega by pi. So in this way we can find the Fourier transform for this signal. So what is the Fourier transform for this signal? If you see, this is what, this is to sync omega by pi. Yes, now see, this is my rectangular signal, which is the shifted version of this signal by an amount of what? 1, by an amount of 1 on the right hand side, so on right hand side, so I will apply the shifting property. Okay, so let's see this signal, let's see, this is my x1 of t, what? X1 of t signal. Okay, so now I can write x1 of t is equal to what? Is equal to, this is my this signal. Okay, so let me write this signal as p of t. So this x1 of t and this is my p of omega. So x1 of t is equal to p of t minus what? Shifted by 1. Okay, so then we will get the signal. So this is what? P minus 1, where p of omega, Fourier transform of this signal is this. Okay, so now I will apply the shifting property here. So then I can find the Fourier transform for this signal. So let me, now I can rub this. Okay, so because I have shifted this and I will get here this signal. Okay, so I will rub this here, and if you see this one x1 of t signal, and by applying what? Fourier transform on both sides, here it is shifting, so shifting in time domain. So if I will apply the Fourier transform on both sides, I will get x1 of omega is equal to this is shifted version, shifted in time domain, which is nothing but e to the power minus j omega. Okay, e to the power minus j omega into p of omega. Okay, so this is what the Fourier transform of this signal. What is my p of omega? This one. P of omega is this. So then I can write here what? I can write here x1 of omega is equal to e to the power j omega into p of omega. P of omega is nothing but to sync omega by pi. Okay, so this is what actually the Fourier transform for this signal. Yes, what we did here, first we took the standard rectangular signal, then after that we know the Fourier transform for standard rectangular signal. Based on that we took the standard signal with the width of 1. Yes, for that we have obtained the Fourier transform this. Okay, so for the width of 2. Okay, so without any shift. Then after that we have shifted the standard rectangular signal with width of 2 by an amount of 1, then we got this signal. Okay, so this signal. So what is actually the Fourier transform of this signal is this one. Okay, so here now I can write nicely now here x1 of omega, here u of t minus what? U of t minus 2. Fourier transform is what? Fourier transform is e to the power minus j omega into 2 sync omega by pi. Okay, so this is what the Fourier transform. Okay, so this is nothing but 2 into e to the power minus j omega into sync omega by pi. Okay, so this is the what? Fourier transform for this signal. So this is the Fourier transform for this signal. Okay, so e to the power minus j omega sync omega by pi is the Fourier transform for this signal. Okay, so in this way we can find the Fourier transform. Okay, so for unit step signal, let me write the standard given signal. So the given signal was x of t is equal to cos omega t. Yes, cos omega, let me write this omega naught. Okay, so omega naught t into u of t minus what? U of t minus 2. Okay, so please write this as omega naught. Okay, omega naught. Now you see, we know also the Fourier transform for co-sinusoidal signal as what? Co-sinusoidal signal is what? Actually it is half half e to the power j omega naught, this is t here, omega naught t, plus half e to the power minus j omega naught t. Okay, so this is what e to the power j omega naught t. Okay, so if we apply the Fourier transform for this, we know the Fourier transform of standard exponential signal e to the power plus minus j omega naught t. Fourier transform for this is nothing but 2 pi a delta of what, 2 pi a delta of omega. Here is plus, then it become minus, here is minus, it become plus omega naught. So this is what standard exponential signal Fourier transform is this, 2 pi a delta omega plus minus omega naught. We will apply this property to here. Okay, so to find the Fourier transform of this cos omega naught t. So what is that? If you see here, now Fourier transform for this is nothing but, I am applying here Fourier transform. As we have seen, the standard exponential signal Fourier transform is nothing but 2 pi divided by 2 into delta of omega. Here is plus, then it become minus omega naught plus 2 pi divided by 2 delta of omega. Here is minus, it become plus. Okay, so plus omega naught. Now see here, this is 2 get cancelled, and we will get what, pi into delta of omega minus omega naught plus delta of omega plus omega naught. Yes, this is the Fourier transform of cos omega naught t. Okay, so now I can write directly. Okay, so this is what here the Fourier transform for this signal is what, this is pi delta of omega minus omega naught, okay, plus delta of omega plus omega naught. Yes, so this is the Fourier transform for cos omega naught t. Okay, so now you see, now we are now available. Okay, so we are now available with both the Fourier transform. Okay, so that is what x of t is equal to cos omega naught t into u of t minus 2. Okay, so you see this signal here is multiplication in time domain correspond to convolution in frequency domain. Okay, so let's see here. Now we are going to apply the convolution Fourier transform. Okay, here this is multiplication, and in frequency domain it becomes convolution. Okay, so that is what Fourier transform of x of omega is equal to, here you see cos omega naught t, Fourier transform that we know very well, what, pi. Okay, so pi into delta omega minus omega naught. Okay, omega minus omega naught plus delta omega plus omega naught. Convolution here, convolution with what, convolution with this signal. For this signal, convolution is, this signal Fourier transform is 2 e to the power what, e to the power, this is shifted version, e to the power on left side, so e to the power minus j omega. Yes, e to the power minus j omega. Yes, so omega into what, into sync omega by pi. Now we have to convolve this, and it is divided by what, 2 pi. Divided by 2 pi is also there. Why? Because we are taking omega. Okay, we are taking the frequency in what, radian per second. So that's why this should be divisible, this should be divided by 2 pi. Okay, if we take the frequency in hertz, then this 2 pi will get eliminated. Okay, so that is, so now in this way we will get the Fourier transform of this signal. So if you see here, pi get cancelled, here it will come 1 by 2 here. Okay, so this is convolution. This 2 will go outside, it become 2 pi will get cancelled. Okay, so we are left with what, now you see here 2 pi get cancelled, and we are left with what, this is my delta of omega minus omega naught plus delta of omega plus omega naught. Okay, convolution e to the power minus j omega sync omega by pi. Okay, so let me write this somewhat here. Okay, so then it will look clearly. So if you see, this is what x of omega is equal to here delta of omega minus omega naught plus delta of omega plus omega naught. Okay, convolution e to the power minus j omega sinc sinc omega by pi, sinc omega by pi. Now you see here x of omega e to the power j omega, we are going to convolve this signal. Okay, so this is what omega equal to omega naught. Now convolution, by applying convolution property, what we know in convolution property, see x of omega convolution delta of omega plus minus omega naught is equal to what? Is equal to x of omega plus minus omega naught. Okay, so this is minus plus omega naught. Okay, delta of omega plus minus omega naught, so it become omega yes, plus minus, same plus minus omega naught. This is what convolution property in frequency domain. X of omega convolution delta of omega plus minus omega naught is equal to x of omega plus minus omega naught. Okay, now we are going to apply this property here, by which we will get here e to the power minus j omega, so it is minus j omega is equal to omega naught. Yes, so e to the power j omega minus omega naught. Yes, so this is e to the power j omega, so this is e to the power j omega minus omega naught. Yes, shifting into sinc omega minus omega naught divided by pi plus here it is omega plus omega naught. Yes, so it is e to the power minus j omega plus omega naught sinc omega plus omega naught divided by pi. Okay, so this is what the Fourier transform. Okay, Fourier transform of this signal. So now what we can do here, can we do something here? Nothing. So this is what the Fourier transform for this signal. Okay, Fourier transform of this signal that we have obtained, like this one. Okay, so finally we can write the Fourier transform of this signal is what? This one, e to the power minus j omega minus omega naught sinc omega minus omega naught plus e to the power minus j omega plus omega naught sinc omega plus omega naught by pi. So finally what we can write, the Fourier transform for this signal is what? The Fourier transform of this signal is x of omega is equal to e to the power minus j omega minus omega naught sinc omega minus omega naught divided by pi plus e to the power minus j omega plus omega naught sinc omega plus omega naught by pi. Okay, so this is what the Fourier transform of the given signal, this one, cos omega naught t into u of t minus u of t minus 2. Okay, so this is the Fourier transform for this signal. So in this way we can find the Fourier transform of the signal. Okay, so whichever the unit step functions, how much shifting is there, we will plot that signal. Then after that we will get the prediction that this is a shifted rectangular signal. Okay, so then after that we will apply the shifting property in Fourier transform. Yes, this is the way to find the Fourier transform of the co-sinusoidal or sinusoidal signal multiplied by the unit step shifted version. Okay, so that's all for today, and thank you very much. Thank you.